Hello and welcome back. In the previous lectures, we were looking at thermodynamic property calculations or changes in thermodynamic properties for over a process, and we looked at calculation of these changes for ideal gases, and then we introduced the concept of residual properties, which are corrections over the ideal gas. And we have looked at how to calculate these residual properties like residual enthalpy, residual entropy, residual Gibbs free energy using virial equation of state. We have looked at how to calculate them using second and third virial coefficients. One of them is going to be explicit in pressure. The other one is going to be explicit in volume. We've looked at both versions for calculation of residual properties. We've also looked at the temperature dependency of B and C, the second and third virial coefficients, and how that affects or how that is introduced into these calculations. And finally, we have introduced the cubic equation of state, and using cubic equation of state, we have calculated the compressibility factor and the molar volume of a fluid. What we'll do in this lecture today is extend these ideas and concepts to calculate other thermodynamic variables such as residual Gibbs free energy, residual enthalpy, residual entropy, etc., using the cubic equation of state. Later on in this video, we're also going to talk about using what are known as Spitzer correlations, and one of the more famous Spitzer correlations are Lee-Kessler tables. So we're going to look at Lee-Kessler tables and how they are used in calculation of various thermodynamic variables. To begin with, let's quickly summarize what we did earlier in terms of some mathematical expressions. We looked at expressions for the Gibbs free energy, and we said we're going to use Gibbs free energy as the generating function. We've looked at expressions for residual Gibbs free energy in both the pressure and volume explicit forms. One of them applicable for the cubic equation of state. More applicable for the cubic equation of state is going to be this one. It's easier to handle these expressions. And based on this generating function, we have also derived the enthalpy and entropy. So if you look at the right hand side, there is the compressibility factor and then integrals in terms of density. In the generic form, if you recall, we have expressed the cubic equation of state via this expression. This is a general cubic equation of state. The expression for A, epsilon, and sigma determine what type of cubic equation of state we have. We looked at 4 different cubic equations earlier, right? So we're going to, these definitions for A and B is something we looked at earlier. In addition, we derive a few other parameters, beta, which is going to be dependent on both temperature and pressure in addition to B, and Q, which will depend on temperature, pressure, and the parameter A itself. Once we have beta and Q, we calculate I, which essentially corresponds to the integral we were doing earlier. As in case of van der Waals, we were integrating it with respect to density. So that I stands for the integral value. And it is different depending on what values of sigma and epsilon we have. And if you look at the table, in certain scenarios, sigma and epsilon are same. In certain scenarios, sigma and epsilon are different. And for each case, we have different expression for I, right? It is given in terms of the compressibility factor Z and beta in addition to sigma and epsilon. Once we calculate all of this, right, then we can go back and use these variables we have calculated to write the expressions out for various residual properties. In particular, for GR over RT, we have already calculated the compressibility factor, the term beta, Q, and I, so I can plug those in there to get GR over RT. Similarly, for HR over RT and SR over RT, there is a derivative term of the compressibility factor with respect to temperature, and the derivative with respect to temperature brings in this additional term square root of TR over alpha. And if you look at the previous slide, this alpha, right, when we take the derivative for van der Waals, A was not a function of temperature, but for other equations of state like these two, it will be a function of temperature. And for these equations of state, we take the derivative and we do the integration. After taking that derivative, we end up with these terms, square root of TR over alpha and zeta, which again is given in the expressions here, right, for SRK and Peng-Robinson equation of state. For others, of course, we don't have the value for zeta. They're not dependent on temperature. So keeping these in mind, what we essentially, we don't have to use these expressions. You can start off from the equation of state, derive like we have done for van der Waals equation of state. We'll still end up with the same result, but it is convenient to have handy expressions such as these, as long as we remember where they came from. And once we have these expressions, it's pretty straightforward to use them in our calculations. So what we want to do is, now let's look at an example. We're going to find the residual enthalpy of propane at 280 Kelvin and 5.8 bar using Peng-Robinson equation of state. If you look at this, if you want to find the residual enthalpy, I need to calculate the compressibility factor Z, alpha, TR, QI, etc. So let's first go back to what Peng-Robinson equation of state is. This is it, right? And then for Peng-Robinson, I'm interested in sigma and epsilon values. They are not same. So when I'm calculating I, I'm going to use this expression for I, because sigma and epsilon are not same. And other equations are same for all equations of state. And of course, for calculating alpha, I want a value for zeta, which will come from here in case of Peng-Robinson. In this scheme of things, the first thing then I want to find are PCE and TC. So I'm going to look up a data handbook or your textbook. For propane, the critical temperature is 369.8 Kelvin. The critical pressure is 42.48 bar. And hence, we calculate the reduced temperature and reduced pressure, P over PC, which in this case turns out to be 5.8173 over 42.48, which is 0.1369. And similarly, TR is T over TC, which turns out to be 0.7572. Once I have these two values and also the value of omega, the eccentric factor for propane from the tables, in this case it's 0.152. Once I have these values, I can calculate zeta, which is for Peng-Robinson, it is 0.37464 plus 1.54226 omega minus 0.26992 omega square. And this value turns out to be 0.6028. And once I have omega, I can calculate alpha, which is 1 plus zeta, 1 minus TR to the power half, whole squared. So I know zeta, I know the reduced temperature, so I can plug the numbers in to get the value for alpha. In this case, this value turns out to be 1.1627, right? I have alpha, I have zeta. The other things I need for in these calculations are beta, which is omega. It is omega PR over TR or BP over RT, whichever one is convenient depending on what we have. In this case, let's just go with omega PR over TR. Both are equivalent expressions. PR over TR. And for Peng-Robinson, omega is 0.0778. PR is 0.1369. And TR is 0.7572. So this beta then turns out to be 0.01407. Similarly, Q is psi alpha by omega TR, and I have all the numbers I need. If I plug these numbers in, I'll end up with a numerical value of 9.02. I have beta and Q. The next thing to find is the actual value of the compressibility factor itself. And in one of the previous lectures, when we looked at using cubic equations of state for finding the compressibility factor or the molar volume, we have written the expression in terms of a cubic polynomial in Z. So let's write that down again. It's Z cube plus Z squared epsilon plus sigma times beta minus 1 minus beta plus Z times beta Q minus epsilon minus sigma minus epsilon plus sigma minus epsilon sigma, and finally the constant term, which is beta square Q minus epsilon sigma beta minus epsilon sigma is equals 0. Now, I have everything I need to get the coefficients of this polynomial in Z. I can put these terms here, and turns out that the polynomial I'm going to end up with is 0.98593 Z squared plus 0.09825 Z minus 1.5861 10 power negative 3. This equals 0. These are the coefficients for the polynomial. I can solve this polynomial, and it turns out this polynomial will give me 3 roots: a vapor root, which is 0.8758, and a liquid root, which is 0.0201. These are the vapor and the liquid roots I have for this particular polynomial. Based on these roots, I can calculate the molar volume. For the vapor, it's going to be Z for the vapor, RT over P. Now recall that RT over P is the molar volume for the ideal gas. So this is the vapor molar volume, right? And this number turns out to be 3.4968 liters per mole. And the liquid molar volume is going to be Z liquid RT over P, which is 0.0849 liters per mole. These compare well with the experimental values, but for this particular problem, what we're interested in is actually the integral I and then calculating HR over RT. We in fact don't have to calculate the liquid and vapor molar volumes. I've just calculated them to refresh your memory on how we have used these to calculate molar volumes. But what we can do is actually take that and now calculate I. The question is, which value of the compressibility factor do I use? The expression for I is 1 by sigma minus epsilon L ln Z plus sigma beta Z plus epsilon beta. So which value of Z will I use to calculate I? Turns out that we can use the vapor value to calculate the residual enthalpy for the vapor phase, and the liquid value to calculate residual enthalpy for the liquid phase. So what we'll do then is, let's say we want to calculate the residual enthalpy for the vapor phase. So we will use the expression for I and replace Z with Z for the vapor, so that what we end up is calculating I for the vapor phase, which in turn will be used in calculating the residual enthalpy for the vapor. So I'm going to plug in this value of Z for the vapor phase, sigma, epsilon, and beta to calculate I. If you recall, this was 1 plus square root of 2 minus 1 minus square root of 2, right, ln of 0.8758, that was the vapor Z, plus 1 plus square root of 2 beta 0.01407 over 0.8758 plus 1 minus square root of 2, 0.01407 again for beta. And if I simplify this numerical expression, what I end up is a value for I vapor. In this case, it is 0.0158. And once I have I vapor, I can go back and calculate HR by RT, remembering that this is the calculation for the vapor phase. If I want it for the liquid phase, I can do a similar exercise but involve the liquid compressibility factor. HR by RT is Z minus 1 plus negative of zeta square root of TR over alpha minus 1 times QI. And if I plug in all the numbers I have, what I end up with is negative 0.3364. This is HR over RT. I can use it to calculate HR. I just have to multiply this number with R in joules per mole per Kelvin, if that is the units I will be using, times T. The temperature I have is 280 Kelvin. So what I will end up is in joules per mole, 783 joules per mole. I can do a similar exercise, use the expressions for GR over RT, right? As in this slide, I can use the expressions for GR over RT or SR over R and then calculate the other thermodynamic residual values if need be. But this would be the general procedure. Just for your reference, the values I have for GR are negative 275 joules per mole and SR is negative 1.815 joules per mole Kelvin. Right. So this is how I will use a cubic equation of state and calculate various residual properties. We have looked at how we can derive the expressions given a cubic equation of state or use the generic expression, the one that is readily available for the 4 different cubic equations we looked so far. So this ends our discussion on using cubic equation of state for residual property calculations. What we'll do next is look at what are known as Pitzer correlations. If you recall, when we introduced the cubic equations of state, we said 2-parameter theorem of corresponding states does not hold well for fluids that are not simple, simple fluids being spherical, nonpolar, etc. But we used a quantity called as eccentric factor and included it in our cubic equation of state, and we said fluids that are at the same reduced temperature, reduced pressure, and have the same value of eccentric factor behave similarly, and we call this as the 3-parameter theory of corresponding states, right? So Pitzer has taken this idea, and what he has done is looked at the behavior of the compressibility factor Z versus the eccentric factor omega. And it turns out in most cases Z is fairly linear function of omega. So what Pitzer proposed is Z can be expressed as a linear function of omega. Z is Z0 plus omega Z1. And these 2 parameters Z0 and Z1 are going to be functions of the reduced conditions, both TR and PR. So in this sense, omega Z will be a linear function of omega, whereas TR and PR will affect both the values of Z0 and Z1. That's how all the 3 parameters contribute to the total compressibility factor Z. One of the famous tables that have been proposed based on this concept are known as Lee-Kessler tables. Taken this from one of your textbooks. I've taken this table from one of your textbooks, and if you see at these tables, the values of both Z0 we talked about and Z1 are listed as a function of pressure, the reduced pressure I should say. It changes horizontally like that, and the reduced temperature changes vertically like that. Similarly, both Z1 also is expressed as a function of reduced temperature and reduced pressure. These are tables for Z0 and Z1, right? So given a reduced condition TR and PR, right, for example, TR is 0.97, PR is 0.2, I can locate what the value of Z0 is going to be at 0.97 and 0.2. Similarly, I can locate what the value of Z1 is going to be at the same reduced conditions. Once I have these two numbers, then it turns out Z is going to be Z0 plus omega Z1. So if I have omega, I can readily calculate 27 plus omega times negative 0.0208. That will be the value of Z. And if you look at this expression for Z, a majority of the contribution still comes from Z0, which is the case for a simple fluid. Omega is 0, this is Z0 comes from the simple fluid contribution, and Z1 is a correction over the simple fluid contribution. It's much smaller than this value. Omega is usually around 0.1, 0.2 at most. So the contribution of the second term is pretty small compared to that of the first term. Nevertheless, it's a correction over the simple fluid correlation. That's how it is corrected using the three parameters TR, PR, and omega. Now, these, like I said, are known as Lee-Kessler tables. What we'll do is quickly learn to use these tables for two different scenarios, and then we'll look at calculation of other thermodynamic properties using these Lee-Kessler tables. What we want to do is calculate the molar volume of propane vapor at 280 Kelvin and 4 bar, right? At 280 Kelvin and 4 bar, remember we have to use the reduced conditions. So the first thing we will be needing is Tc, Pc, and omega. For propane, omega is 0.152, Pc is 42.48 bar, and Tc is 369.8 Kelvin. Once I have these values, I can calculate TR and PR. TR in this case turns out to be 0.7572. This is T over Tc. And PR is 0.09416. This is P over Pc. Once I have TR, PR, and omega, I can actually go back to the tables and look for the value I'm after. So 0.7572 is my TR. And if I look at this table, let's pick that, 0.7572. So it's going to be, this is 0.75, this is 0.8. So it's going to be in between these two rows, and the TR value we calculated, maybe I should just write those TR and PR from there here. It might just be easier to work with, but anyway. And the TR for this problem we have is 0.7572 and PR is 0.09416. So it's going to be in between these two values here on the vertical and between 0.05 for PR and 0.1 for PR, right? So it's going to be between these four numbers, somewhere in between there, right? So I have to do a linear interpolation, and in this case, I don't have the numbers for the exact TR or for PR, so what I will end up doing is what we call as a double linear interpolation. So we're going to do a linear interpolation on the pressures first, and then on the temperatures, or we could do it vice versa, right? So what we will do is write these numbers. TR is going like this, 0.75 and 0.8. I have it at 0.75 and 0.8. I'm interested in 0.7572. I have it at a pressure of 0.05. I also have it at a pressure of 0.1, but what I'm interested in is at a pressure of 0.09416, right? So let's first fill in the details we have at the four conditions. 0.75 and 0.05, I have it as 0.9598. These are values for Z0. and at point 1 it is 0.9165. At point 8 and 0.05 this value is 0.9669, and this value here is 0.9319. What we'll do is do a linear interpolation between 0.05 and 0.01 to get at 0.8, but then at this PR. TR is still 0.8, but at this PR, which means I just need to do a regular linear interpolation between these two values, and that gives me a value of 0.9360. Similarly, I will interpolate between these two values to get at a condition of 0.75 for TR and 0.09416 for PR. And if I do that linear interpolation between these two numbers, what I will get is 0.9216. So now I have it at a pressure, at the required desired reduced pressure, but at two different TRs. I need to do a regular linear interpolation between these two numbers again to get it at the TR I'm interested in, 0.7572. And if I do that between these two numbers to get it at this condition, it turns out to be 0.9236, right? So this is the number I'm after, 0.9236. So what we have done is a double linear interpolation to get this number, right? So that's how we do a double linear interpolation if I have a table to get it at the condition I'm interested in at TR and PR of these two values, right? Similarly, I can do a double linear interpolation for Z1 between the pressures that are in the table. If we go back to the table, for Z1, again, it's the same reduced temperatures and reduced pressure. So I'm looking at a double linear interpolation between these four quantities, and if I do the double linear interpolation for the desired reduced temperature and pressure, what I have is a value of negative 0.0662. And once I have Z0 and Z1 from the Lee-Kessler tables, I can calculate Z. It is Z0 plus omega Z1. So it's going to be 0.9236 plus 0.152 times 0.0662, negative of that. And that will give me 0.9136. And if I were to calculate V using this, it will be Z RT over P. Again, remember RT over P is the ideal gas value, Z is the compressibility factor, and if I simplify, what I have is 5.317 liters per mole, and it turns out experimentally measured value for these conditions is 5.338 liters per mole. So pretty close comparison using the tables, right? So that's how I'm going to use Lee-Kessler table to calculate molar volume and compressibility factor. Let's look at another example. Find the molar volume of propane at 277.35 Kelvin and 16.992 bar. We still want to use the Lee-Kessler tables. We'll do a similar exercise as we have done earlier and quickly calculate TR, which is T over TC, and in this case it is 277.35 over 369.8, turns out to be 0.75. Luckily, we don't have to do a linear interpolation in this case, at least it looks like so far. This is P over PC, which is 16.992, over PC is 42.48, so I have a value of 0.4. Now, remember omega for propane is 0.152. So let's look at the table. 0.75, the values we listed were 0.75 for reduced temperature and 0.4 for reduced pressure. Let me see where I can find these numbers. 0.75 for reduced temperature and 0.4 for reduced pressure. 0.75 and 0.4. Now, if you look at the tables closely, they are marked differently than rest of the tables. Everything in the table, right, this part, 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 right? Everything above this yellow line I have marked is actually in italics compared to rest of the table, and actually that is to indicate that we are looking at the liquid phase as opposed to the vapor phase in rest of the table. So wherever you find these Lee-Kessler tables, you're going to find a region of TR and PR where the Z0 and Z1 values are marked differently than rest of the table, and wherever you find this region, this corresponds to the liquid phase region, right? And for our particular scenario, we're looking at what we marked for TR of 0.75 and PR of 0.4, we are in the liquid phase region. And we can look at the values of Z, they're pretty small, corresponding to the low liquid volumes, and Z0 we have is 0.067, and Z1 we have is negative 0.0282. If I calculate Z here, it's 0.0627, and the volume is ZRT over P still. It's going to be 0.0851 liters per mole, and the experimentally measured value is 0.0839. Again, pretty close even for the liquid phase calculations, at least in this case. So these tables in that sense can be used in the liquid phase region also, but one needs to be careful. So that's how I can use Lee-Kessler tables to calculate the molar volume and compressibility factor. In fact, not just for molar volume or compressibility factor, Lee-Kessler tables have been developed for enthalpy, entropy, and once we have enthalpy and entropy, we can calculate all the other thermodynamic variables from there. So the expressions are a little different for entropy and enthalpy. For example, enthalpy is written in terms of not HR, but rather HR by RTC. So the total enthalpy, residual enthalpy contribution over RTC comes from two terms, HR naught term and an HR1 term. It's still linear function of omega, but then unlike Z, we have the denominator in this case, which is RTC. Similarly, and the tables themselves, you will find the tables for HR naught by RTC directly, and the tables for HR1 by RTC. Once you have the two tables, you can combine them using a centric factor, and we'll end up with a value of HR naught by RTC. If you're interested in HR, we just need to multiply it with RTC. Similarly, for SR over R, it will be SR naught over R. Again, you will find a table for SR naught over R, and then you will find another table for SR1 over R. Multiply it with omega, add them to get the value of SR over R. Once we have SR over R, we can calculate SR, right? So similar to tables like the compressibility factor, Lee-Kessler tables exist for residual enthalpies as well as residual entropies. They can be directly used to calculate the residual values. In that sense, they are convenient, but then we need to do a linear interpolation or a double linear interpolation as need be. Dealing with elaborate equations, Lee-Kessler tables in that sense are handy. In fact, as we have seen earlier, the contribution of the second term in these Lee-Kessler tables is pretty, well, it depends on the condition, but it is smaller compared to that of the first term. So for a very quick first-hand calculation, one can in fact get away looking at values of Z naught or HR naught or SR naught, etc. for the simple fluids. That will give a quick estimate. So with that, we end today's lecture. We have looked at calculation of residual properties so far using a variety of methods. We looked at virial equation of state, we looked at cubic equations of state, the generic cubic equation of state, we looked at thermodynamic tables, thermodynamic diagrams, and finally the Lee-Kessler table. Thank you.